Hello, good afternoon. Thank you for your attention, and thank you for having me here at BITS. The conversations have been fantastic, and I have the pleasure to present it's not even at the working paper stage, so the feedback here will be invaluable for me and my co-authors, so thank you in advance for that. Okay, so it does work. Wonderful. Okay, I have the privilege to present statistical significance in science mobilization evidence from 10,404 hypotheses in leading health journals. First and foremost, this is joint work with a couple of co-authors, Abel Berdeur from the University of Ottawa, Anthony Hayes, who's now at the University of Birmingham, Taylor Wright at Brock University, and I'm Nick Cook, and I'm from Wilfrid Laurier. I like talking about this paper in terms of its second research question. So its second research question is, does the statistical significance of research affect the attention it receives? We'd love to have a measure of impact. Attention is more feasible for now. So we're going to stick with this concept of attention it receives. And I think I'm going to be somewhat unique in using humor to motivate my start. And I'm going to use an XKCD comic because of just how relatable I think this research project is. So we have here in the first panel is we have our journalist who's wearing a ponytail who comes up to the main character and says, jelly beans cause acne. Of course, perhaps a ridiculous claim, but the question is, scientists are then commanded to investigate. And the scientists, wearing safety goggles as they should, find no link between jelly beans and acne, and the p-value is greater than 0.05, so statistically insignificant result. But then the journalist returns and says, I hear it's only a certain color that causes it. And the scientists are then immediately commanded, despite their protestations that they wish to play Minecraft instead, we should probably look into it. So like good scientists, they go back to the lab and they find no connection between, I'll be brief here, salmon, red, turquoise, magenta, yellow, gray, tan, cyan, jelly beans, and acne. But when it comes to green jelly beans, there is a statistically significant relationship between eating jelly beans, green jelly beans, and having acne. Whoa, this is p-value of less than 0.05. And I'll note immediately, in keeping with XKCD, there are 20 panels to this cartoon, with one of them being statistically significant at the 5% level. So that settles that, because in the next day, the headline is that green jelly beans cause acne. There's a 95% confidence of this happening and only a 5% chance of this is coincidence. Now, we can keep with the humor for now, in that once selectively health-conscious people stop eating those jelly beans, later observational analysis might actually confirm that eating green jelly beans cause acne, which is a mechanism that Oster gave to us in her 2020 AER Insights, which found that health recommendations are selectively followed. And the fact that they're selectively followed means that we're going to end up having dynamic selection, and that dynamic selection then goes ahead and confirms it. So green jelly beans, by the way, might indeed cause acne. So that's kind of the motivation behind this, is the attention that research gets might bias the later observational analysis that you could actually end up having. So what I said that this is two research questions. The first one I'm going to talk about is the kind of inveterate p-hacking and the publication bias, which thank you, Stefan, for showing the first version of some of the pictures. Does the statistical significance of research affect the likelihood of publication? Because it's not the focus of the working paper at the moment. I'll try to be brief about that. We're going to find that, yes, it does. We have publication bias. We have evidence of the first file drawer. We'll be brief about that. And then, does the statistical significance of research affect the attention it receives? Again, the answer is yes. We're going to call this, for today, attention bias. And I'm going to coin it, or try to coin the concept of the second file drawer, right? We can measure the scholarly output and then see what ends up being in the public domain. So we're going to find this is going to be indeed the case for an index of attention. And then I'm going to break down that index into some of its component parts, such as news, social media, and policy. And we're going to find an effect of around a third. So just going past that statistical significance threshold means you're getting 33% more attention and possibly dynamic selection afterwards. And we're also going to find the case it's not part of the attention measure, but we also have data on academic readership via Mendeley and citations. And we're going to find that roughly similar effects. Okay, so I like I like to use a quote, especially for the first file drawer. So because scientists tend to report, it's a quote, hang on, only studies, which would be publication bias or analysis p hacking that work, readers must then be left asking, are these effects true or do they merely reflect selective reporting? I'm going to modify this quote. I'm going to pick on journalists, despite the fact that they're not the only ones. In the second file drawer, we would have, because journalists tend to only report studies, attention bias, that work, readers must ask, are these effects true or do they merely reflect selective reporting? So we're just trying to extend that logic of the first file drawer to the second file drawer and moving towards this level of attention that science seems to get. Publication bias has been detected in many different literatures. My apologies, I haven't cited as many people as I should have in this. The idea, for example, in clinical research will be important for us later, as early as 1991. Political science, which gave us the caliper methods, sociology, psychology, and then economics. And a variety of tools. So a lot of those in the top list give us tools in the bottom list. For example, the caliper method, Simonson et al. From the first file drawer gave us the p-curve. Elliott et al. Gave us additional tests based on the p-curve that are more highly powered. And then we have Stanley, Ducey, Lagos, and Andrews and Casey, which give us meta-analyses and correction, identification and correction for publication bias. But there's plenty more that we can definitely cite here. This detection with a variety of tools has led to what I think are some fantastic titles, Nature, Human Behavior, and I think the American Statistician redefines statistical significance, scientists rise up against statistical significance, and abandon statistical significance, all in efforts to very carefully say, we should be changing the paradigm with which we're reporting things. Again, this is the publication bias section. When it comes to attention bias, we haven't really found anything else that anyone else that's kind of working on this. But our outcome variable, this alt metric, do I have the definition here? Yeah. This alt metric, this measure of attention, the idea behind the alt metric measure of attention is that it's qualitative data and it's meant to be complementary to the citation-based metrics. And is that all that's written there? The citation and the kind of readership metrics that we've seen before. But previous research seems to have focused only on the correlation between these alt metrics, so like social media engagement, for example, with your research, and the citation metrics. What we really care about is whether or not the statistical significance of your result is actually causing people to pick it up. Citation counts, for example, citation counts, journal impact factor, access counts, open access, and press releases are associated with higher scores. So we have this known variable, this alt metric score, and it seems to be correlated with certain things, but let's see what happens when we think about the statistical significance of the underlying result. To answer our research question, the ideal data is feasible to collect so that we can get a large group or a large series of observations. But importantly, and I think in keeping with one of the first panels that we had today, it's going to express statistical significance in a consistent manner. Not only is this is very important so that we don't have errors as we collect, and we're going to choose a particular literature that helps us quite a bit. And indeed, we want a little bit of variation, hopefully lots of variation or outcome variable. So we're going to want a literature that often generates media and attention. Economics doesn't seem to be the case. We're going to have a magnitude, I think, of divide by 10 compared to this literature to economics. So we're not going to use economics for this, my field. Okay, we're going to choose a subset of the medical literature. And the reason we choose a subset of medical literature is because it's consistent with all three of these goals. First and foremost, and I'll show you an example in a second, in the medical literature, you present structured abstracts with key results in the abstract. And not only are the key results in the abstract, their statistical significance is in the abstract. So that means it's very feasible to collect, very quick to collect, and with a lot less errors. Report statistical significance in a consistent way. It's going to be 70% confidence intervals, 30% exact p-values. It's fantastic for our purposes. There's no coefficients divided by standard errors to work with here. Okay, and I mean, during and after the COVID-19 pandemic, I think we've all read one or two articles based on COVID-19. This medical literature often generates media attention, especially during and after the COVID-19 pandemic. So we're going to have lots of variation on our outcome variable. And in particular, we're going to, just to be specific, we're going to use 2016 to 2022 inclusive of the British Medical Journal, the Lancet, and the New England Journal of Medicine. So some of the top journals in that field. What are we going to do in order to get our results? We're going to keep the results section. I'll show you an example in a second. We're going to identify every instance that there's a p-value, so any inequality or an equality. After we've identified all p-values, we're going to identify all confidence intervals just using a grep or a grepl, number dot number to number dot number. And then we're going to make sure to differentiate between ratio statistics and difference statistics and apply the appropriate null hypothesis so that we can convert that into a p-value as well. And we're going to manually audit these abstracts. And after doing something to the tune of 2 to 300, I never found an error. So it was surprising how good the quality of the data was coming from them. So credit to the medical professionals for that, in terms of how easy it was to manually and automatically and manually parse the data that was coming out of these abstracts. This is an example of an abstract from the British Medical Journal. We're going to focus on the results section. So that's the section right here. I'm going to zoom in for us. And as I zoom in, I'm going to highlight in red boxes the 3 statistical significance tests, test statistics that they're introducing to us. So for example, I've got a ratio test, which has a 1.33 with a confidence interval attached, a difference, and then another ratio. So these are going to be 3 observations in our data set. And I'm going to pair that with the altmetric data that's on the right-hand side, so conveniently presented, of 373. This 373 represents a weighted average from altmetric.com, the company that produces this sort of measure. For example, if you are picked up by a traditional news outlet, New York Times, for example, you're going to get an extra score of 8. If you're picked up by a particularly influential blog, you're going to get an extra score of 5. For each tweet, is there a pointy thing on this? So the big one? Okay. For each tweet, for example, you're going to get 0.25. That's going to be discounted if it's repeated tweets from the same place or if it's a bot. So there's some clever bits that altmetric.com is going to try to do. So we're going to use the index from altmetric, but we're also going to break it down into its component parts to make sure that the weighting isn't actually driving anything. And, maybe news acts differently than social media. So we're going to do that. And again, we're going to have Mendeley readership, and then from Dimensions, which I think uses AI now to collect citations, we're also going to have information on that. So that's what I'll be presenting to you today. Our data at a glance, the average p-value is not statistically significant. So it's a 10 at the 10% level. I guess in econ, we'd give it 1 star. 70% proportion is confidence intervals, 30% exact p-values. I like, for example, the fact that we have 6 tests on average, and only 11% are going to mention COVID-19 because we're going to collect from 2016, 17, 18, 19. So there's going to be plenty of lead time before that kicks in. And our standard altmetric score is going to be 857.33. Instead of showing you a mean, I'd rather show you the distribution. The idea being here that 857 of a mean is hiding just how long and thin that right tail is. So there are some, I think I got 10% here. There are some articles that have a lot of attention, that are generating a lot of attention, whereas most of them, or let's say 50% of them, have less than 327. And this is going to be true whether or not I just show you by observation or at the article level, or indeed even the component parts are going to have the exact same kind of behavior. This distribution of our outcome variable is not going to change much by method or by journal. It will change by year for the fact that we have on the board here. Pre-COVID, we have an average score of around 700. Non-COVID, which is going to be used by text analysis, we're going to make sure there's no COVID or SARS-CoV in there. That's going to be anything that's 2020, 2021, and 2022 has roughly the same amount of attention given to it. But if it's a COVID-19 article, you get a lot more attention. So all of our results today are going to be robust to the inclusion of COVID-19 fixed effects, but just wanting to highlight the fact that this could be driving something, but it isn't. So now that we're familiar with the data, we can ask our first question, and does the statistical significance of a research result affect the likelihood that it is published? We're going to first and foremost define what statistical significance is in this literature. In economics, we put our first star. We have our first bit of statistical significance at the 10% level. Let's see if that's the 10% level or the 5% level for medical. For example, here we have a p-value of 0.06. And our conclusion in our abstract is that this did not significantly reduce the incidence of death from any cause among men 65 to 74 years of age. So we have a single candidate that says 6% is not statistically significant. One of my favorites is the following: a fantastic, just thinking about the design of the research, 20 years of following up on how many people? We're talking 223 of 364 men and 245 of 367 men. So hundreds of patients. We have a p-value of 0.06. We have a reduction of I think it's around 4 percentage points. If you take the 11.4 minus 7.4, 4 percentage points, give or take a 50% reduction in your mortality from localized prostate cancer. Large, huge, p-value 0.06. After nearly 20 years of follow-up among men with localized prostate cancer, surgery is not associated with significantly lower all-cause of prostate cancer mortality in observation. So we're tossing this into the file drawer, despite the fact that it could save lives just because we have a 0.06, and after 20 years of effort, right? So our candidate measure here is going to be the 5% level. So we're going to stick with that for now. As you move from left to right here, I'm using the absolute as compared to the non-absolute T statistic or Z statistic. So as I move from left to right here, I'm going to have more and more statistically significant results. Here's a histogram of them. And as soon as we get to that 1.96% level in the medical literature, I have a modest uptick in the percentage of test statistics that seem to be, statistically significant. That extra, which I'm going to look forward to correcting for later, with that new method. That extra bump or extra mass seems to continue being there even after the 1% statistical significance threshold at 2.58, and seems to calm down back to a monotonically decreasing distribution after 3 or so. This is going to be the Z statistic distribution. Let's show the exact same. I'm going to zoom in though. I'm not going to show 0.15 all the way to 1. So I'm just going to zoom into the 0.15. Here's your p-values of the exact same distribution that you were seeing before. Here, we're going to really think about comparing, for example, for publication bias. I'll compare just to the left and just to the right of the 0.05. And it seems like there's a large jump when you compare just statistically significant versus just statistically insignificant at the 5% level, for example. The 0 to 1 here is going to embed very high effect sizes. So we're going to focus on that 5% level. Okay, so let's not just focus on data visualization. Here, I'm going to use the caliper tests of Gerber and Malhotra. In one of my papers, I also call these randomization tests. Upon further reflection, they're essentially the same thing, so I'm going to give them credit instead. Proportion significant in the threshold plus or minus 0.4. So if I look at the 5% threshold and look at a relatively wide 0.04, test against a probability of there being a 50% on either side, so it's just a simple binomial test, we get a statistically significant result that it's not 0.5. Let's do narrower and narrower bandwidths, and I'm going to find it's not 0.5, right? And it should be under an assumption that should be around 50 in a sufficiently narrow band. And that's going to be true of the 5% statistical significance threshold and the 1% statistical significance threshold as well. Using newer techniques, Elliott et al. Gives us for the 5% threshold on the left-hand side, the 1% statistical significance threshold on the right-hand side. There's 7, is there 7 or 8? 7 tests. So usually Fisher's doesn't give us too much, but 1, 2, 3, 4, 5, 6 all give us statistically significant evidence that there's publication bias at the 5% level. On the right-hand side, I think one of them doesn't return us the binomial, but other than that, we have 4 tests, which are telling us there is statistically significant publication bias at the 5 and 1% level. So that's our first research question. Is there indeed publication bias? It seems to be the case. Now that we've answered that, if you're published, does the statistical significance of your research affect the attention it receives? So the first thing I'm going to do is I'm going to visualize again. And in this conversation, just because we have a limited amount of time, I'm going to focus on this 5% statistical significance threshold. On the left-hand side, or sorry, on the horizontal axis, I'm going to use the same kind of setup as the p-value curve. And then on your vertical axis, I'm going to have the altmetric score, right? The dependent variable we're going to start with. And if we look at the 0.05, what I've done is I've binned, taken the average of the altmetric score for everything that's just to the left of 0.05 and everything that's just to the right of 0.05. And we're going to be comparing where marker size, of course, reflects the amount of the test statistics that they're responsible for. Just to the left of 0.05, it seems like there is, what's the number I'm looking for? 1250, maybe 1400, give or take. I'll zoom in a second. Whereas if you're just to the right of the 0.05, statistically insignificant, you have much less attention garnered to you. Let's zoom in. So now we can see it's roughly something to the tune of angles here, a bit odd for me. So I think it was 700 and 1400. But I'll let the actual numbers speak for themselves in a second. So that's around the 5% statistical significance threshold. This is around the 1% statistical significance threshold. Let's move on beyond data visualization. My first setup is going to be just comparing levels. So I'm not going to throw out, and I'm not going to use marginal statistical significance yet. What I'm going to do is on my left-hand side, I'm going to have the altmetric score or a component of the altmetric score. Then I'm going to care about two coefficients of interest. The first coefficient, beta 1, is going to be the estimated linear probability model coefficient on an indicator variable, which takes a value of 1 if and only if the test statistic is statistically significant at the, at the 1% level. I think I can handle it. Okay, and then the second one is going to be the same at the 5% level. And the reason I think, and we're going to include year fixed effects and journal fixed effects in gamma and iota respectively, and we're going to cluster standard errors at the article level. This is why I think I can handle it. Nice small tables. Here we go. In column 1, if you are statistically significant at the 1% level, as compared to everything that's not statistically significant at the 1% level, you get 259 more altmetric score. It's somewhat meaningless until we use the average altmetric, which means we're looking at a coefficient around 30%. This is why, if we use the 5% statistical significance threshold instead of just the 1, compare 5 against not, we get 31%. And if we put in both at the same time, we're going to get 35 and 13%. We're going to find roughly the same characteristics if we add in coarsely reported, so the p less than 0.05, p less than 0.01s, COVID-19 by method primacy using the logarithm, and we don't need to include these fixed effects. Here's the components. The first component, for example, is the traditional news outlets. We're just going to use that standard setup, 37 and 17%. Twitter, it was still called Twitter at the time, 36 and 6, but we're not seeing statistical significant right there at the 5% level once you have both controlled for. Facebook, which are publicly curated or very carefully curated by altmetric Facebook pages. These aren't Facebook users. These are Facebook news pages. Doesn't seem to have any effect. Policymakers seem to like the 1% statistical significance threshold, but that might be rational in a second. And then Mendelean citations, so academic readership and academic citations. But it could be possible that it's rational to pay attention to things that find an effect versus not an effect. So the idea here is to look at marginal statistical significance, i.e., is it rational to pay attention, so much more attention to something that has a p-value of 0.049 versus 0.051? So we're going to apply that same kind of marginal statistical significance idea to this altmetric outcome variable. Now I'm going to have a single regressor of interest that I'm interested in, this beta 1, which is going to be on an indicator variable, which takes a value of 1, if you're statistically significant, in a small window around the threshold, right? And here I'm going to denote that using omega. If you look at the 5% statistical significance threshold, we're going to find 26, 38, 35 as I shrink that window. So as I shrink it down to the smallest one that I'm offering here today, 35%. And if I look at the 1% statistical significance threshold, I'm going to find 25, 24, 26%, call it a quarter. So we're looking at very, very tight bands around that. And this is going to be true at the 5% level for news, social media, Mendeley, not really citations. And at the 1% level, we're going to see something to the tune of, we're going to find statistical significantly results, news, Twitter, policy, Mendeley, and citations, like we saw with the plain OLS, like the non-marginals. And we're going to see a little bit of heterogeneity, 19, 33%, 32% for policy, Mendeley, and citations. But overall, we're going to call that about a quarter if I had to put a single number on it. So what I'm going to do is I'm going to leave you with one number in one sentence if I can, and that is statistical significance seems to increase overall attention. And then its components, news coverage, Twitter engagement, policy impact, academic readership, and indeed citations by around 33%. And if you're careful to use only the marginal statistically significant effects, we're looking at around an increase of around 25%. And I guess extra questions. Thank you.
This may be impossible, but I was just so struck when you showed that, like, that huge study with a p-value of 0.06 and then the conclusion, not significant. Just knowing that, not all doctors have had a lot of statistical training. Is there any way to trace this through to somehow, like, how patients are treated through, like, looking at, for example, clinical guidelines, like this? I just like, would the takeaway from a doctor reading that study be like, we shouldn't do whatever that intervention was? Because if yes, that just seems like that would be, worse than the news coverage of it is just if it distorts how patients are treated.
Yeah. The very beginning of what we talked about today is that your research affects lives, right? So a great way to think about that. In the literature review we were talking about, there is That's one of the reasons why we have these. Amrine et al. 2019, 800 signatories, right, are calling for the end or statistical significance because you're dismissing possibly crucial effects. And that's exactly the argument that they raise, that we're not following up. But yes, I think that that would be a completely feasible research plan to actually look at that, is to look at the medical professional kind of guidelines and then whether or not they get updated afterwards. Yeah. Yeah. Okay, that's excellent. We should talk offline after. Thank you.
I just had a question about your first p-value versus alt metric. So there was 3 outliers on that had p-value greater than 0.05 that were like really high alt metric scores. I was wondering if you like knew whether those were like specific, I don't know, like other pandemics or something that had like such a, that one, yeah, there's like at the very top, like why that may have been. That was if you had that.
I'm going to say that those are like highly influential papers that aren't statistically significant. But this is all test statistics coming out of, right? So because these are binned, these guys might share some p-values in here, but the averages are hiding it, right? I suppose the other way to do that would be to not bin it and go from there, but then I'd lose the visualization here. Yeah, I'm going to say these are highly influential studies, probably in that really thin right-hand tail. I think in the working paper, when it gets released, we'll probably like say which of these papers are, and really delve into it, just make sure that those aren't driving anything. Good observation. Thank you. Yeah. Stefan.
Yeah, and you may have already said a little bit about this, but can you tell us a little bit more about, like, in your mind, how much should statistical significance affect reporting and attention and action? Like we could think of statistical significance as a decision problem, right?
Mhm.
So it should like change some of our decisions. So in your mind, what are the decisions that it should change and what are the decisions that it should not change? Like publication maybe is
It
something.
should change this one, in my thinking. I think this paper has it right, or this abandoned statistical significance, which I think some people in the room are actually part of. It should be, p-values should be demoted from the screening process that it makes and instead be part of a suite of things that we as referees evaluate. So like effect size and importance and credibility of the design. I think that those should all be considered, rather than like lexicographic preferences of, is it statistically significant? No, reject, versus, we should probably be thinking about other things as well. Yeah. Thank you.